Okay, so now how do we draw the circuit? We will. So this is how from the equation we have drawn the circuit here. How it is drawn? You see here that dA is given as AX plus BX. Am I right? And this is an example for a JK flip-flop. If you want me to draw it for this one, this particular circuit, I'm having A flip-flop, which is a DA flip-flop. I'm having DB flip-flop, DB as an input and a B flip-flop, and my output is going to be AB X bar. Okay, so this is my output A and this is my output B. DA will be given as X is your input, AX. This is my AX, and of this, and BX, B and X, and of this, the OR operation is fed to DA. So this is done. DB A bar X. Where is A bar? A bar, this is A and this will be A bar. Am I right? The complemented operation. I can take it directly from here, or I can put a NOR gate, but putting a NOR gate will add one more gate to my circuit, which will add cost to my circuit. So I can take the complemented output, Q bar output. So this will be A bar, and this is my X. And of that, I'm giving it to DB. So what is Y? Y is nothing but A and B here. I'm sorry, I'm just drawing, and X bar also, right? So this is OR operation and then X bar. So take a note of this and then AND it. So this will be my Y. Right? So this is how you draw the circuit diagram. Okay. Now let us take another example, which is a JK flip-flop. What is given here is, please listen this particular class. We are doing we are going to do reverse engineering now. So this is the sequential circuit that is given using JK flip-flop. So what are the things that you require for drawing a state table? You will require present state. Present state is nothing but Q of t. So since we are having two flip-flops here, we are going to write it as A of t and B of t as our present state. What is what is the thing that you require? Your input, right? So on your input side, you require A of t, B of t, and your inputs. And on your output side, what are the things that you require? You require A of t plus 1, which is your next state, B of t plus 1, which is your next state, and if there is any external output, you don't have any other external output. In addition to that, you will require, since you don't have any output equation, this is not applicable as far as this particular circuit is concerned. So these are the things that are required for you to, present state is required, your input is required, your next state is required from the state equation, and your output is required. So yeah, since we are using a JK flip-flop, we have to write the flip-flop input equation separately here. Whereas in the previous case, since these are D flip-flops, your next state is similar to your D flip-flop input here. So it is going to be slightly different in this particular case. Please listen carefully that when your flip-flop is other than the D flip-flop, either it is JK or T flip-flop, it is necessary to refer the characteristic table and characteristic equation to obtain the next state values. Let us see how. Now, you have to determine the flip-flop input equations in terms of the present state and your input variables. List all the I think let me go directly to, um, yeah, okay. Okay, now why in the previous case we just had a D flip-flop, right? Whereas here it is a JK flip-flop. So your JK flip-flop will have a different input equations for JA and KA. Why? Because J and K has got a different characteristic equations. Similarly, JB and KB will have a different characteristic equations, next state equations. So hence, first your input equations for your JK flip-flop is given like this. Let us consider that these are the uh, input equations. If you want, you can look from the diagram also. JA is equal to B, right? So you can see here that JA will be directly connected to B. So JA here, it is directly connected to B. And KA is nothing but, what is this KA? This is X bar here, and this is B. So X bar B will be your KA. Okay. So X bar B will be your KA. Likewise, we have for JB and KB also. Now, how do we fill this state table? You are similar to the previous case. These are your inputs. So present state, which is nothing but Q of t, and your all possible inputs. List down all the possible input combinations. Okay. Now, there is a slightly a different case here. Don't fill the next state immediately. Okay. So this next state has to be filled with the characteristic equation. Okay. So this two columns must be filled towards the end only. Now come to the flip-flop input equations. How many flip-flops are there? There are two flip-flops which are J and K, J and K. And since we have two inputs for two flip-flops, we will have JA, KA as input of A flip-flop and JB, KB as input of B flip-flop. Okay, so now, so this is the first thing that you will do. You will fill all the input row combinations. Then you will come back to the flip-flop input equations. You will use these equations that was given from the circuit to fill up the JA, KA input values. So you see here the JA is equivalent to B, right? So this is the B column. JA will have similar to the B column 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. Similarly, JB will be a complement of X bar. JB will be a complement of X bar, right? So what is X here? 0. So this is 1. This is 1 here. This is 0 here. This is 0 here. This is 1 here. So it is a complementary. So you fill up these inputs based on the above flip-flop equations here. Now you will fill the next state equation. As marked here, you will fill this particular two columns only towards the last. Enter it at the last. Okay. Now, how do you fill this? In order for this to fill, you need a characteristic table which is on page number 190. And what is this particular characteristic table? I'm already having that for you. Yeah. This is what is it? This is page number 190 of my notes. And this is what is the characteristic table is. 190 characteristic table is. What does your characteristic table has? Your present state, your J input and K input and Q of t plus 1. So when your J input is 0, 0, your present state is no change. So you have to use this equation to fill up these rows. Okay, maybe, okay. How do you do that? If you are looking for the A flip-flop, you have to look only at the present state of A and the next state of A only. Okay. So when your present state is 0, so look at this particular table. Your present state is 0 and J and K values are 0, 0. Your present state is 0. Okay. Your J and K values are 0 and 0. So then there will be no change from your present state, right? So there is no change from your present state. Now let us come first to fill up the JA, KA columns and then let us come. Again, when your present state is 0, 0 and your present state is 0, there will be no change. When your present state is 1, 1, look here, it is going to toggle, right? When your present state is 1, 1 and if your present state is 0, it will toggle to 1. It will toggle to 1. When it is 1, 0, you are resetting whatever maybe, you are not bothered about your present state value, so you are resetting it to 1. If you want, I'll go back to the page 190 and show you. So for 1, 0, let us see. For JK value 1 and 0, for 1 and 0, whatever may be your present state value, it is not bothered. Your next state value is always set. Okay, so that's what we have done here. 1, 0 is set. 0, 0, there will be no change. right? No change means if this is 1 here, if this is 1 here, this will be 1. Maybe we'll make it 0. When it is 0, 0, there is no change in the sense it will be 1. It should be 1. Okay, I'm not sure that's when it is 0, 0, again there should be no change from your present state. So this should also be 1. Okay. Now when it is 1, 1, your 1 will get toggled. So this is 0. When it is 1, 0, I am setting my flip-flop. So this is 1. Likewise, when it is 1, 0 here, you have to look now at the B present state, this particular present state. 1, 0, you are setting it. 0, 1, you are resetting it. 1, 0, you are setting. 0, 1, you are resetting. 1, 1, it is going to toggle. If this is 1, then this will toggle to 0. Don't worry about the mistakes. We are correcting it. 0, 0, there should not be any change. So this should be 1. 1, 1, there should be a toggle here. So 1 gets toggled to 0. Okay. And 0, 0, there should not be any change here. So 1, this becomes 1 here. Okay. So there are a few mistakes in this. So these are the correct nodes. Okay. Now we have created a state table, and immediately what next? It is nothing but your state diagram. So state diagram you can draw here. Your present state is 0, 0. The present state is 0, 0. And when your input is 0, you are moving to 0, 1. When your input is 0, you are moving to 0, 1. Why there is no output here? Normally it should be an output slash some output, right? Because this particular circuit does not have any external output here, right? So we don't have an output column also here, right? So hence we need not fill this output column. We need not write the output sequence here also. So for an input of 0, it goes to 0, 1. Now, when your input is 0, 0 and your input is 1, it stays in the same state, which is 0, 1. Likewise, you create your state diagram. And again, please note that there is no output that is given, hence the no outputs are there. Any doubts here? Next, we are going to look at the analysis of T flip-flop. Now, again, there is nothing difficult here. Everything is the same. Only thing is your flip-flop input equation will change. Okay. The first step, your sequential circuit is given and it has got a D flip-flop and it has got an input X also. So first, what is your next state equation? TA. There are two flip-flops, so I am writing it as TA here. What is this equivalent to? This is equivalent to X dot, and the other input is coming from B, so this is X dot B. And this input TB will be equal to just X because this is directly coming from X. And your output Y. So your output Y will be equal to A of T. Obviously, these are present states. A dot B. Right? This will be your output. Okay. Now we have got our equations, the excitation equations. Once we have our excitation equation, we have to draw our state table. Your state table will have what? Your state table will have your present state, A of T and B of T, and your input X. And then you will have your next state will be here, but we are not going to fill this particular next state here. A of T plus 1, sorry, and B of T plus 1 will be your next state, and then your flip-flop input equations. Flip-flop input equations. In addition to that, I'm sorry, I don't have space here. You will have an output equation for Y also as a last column. So first thing is you will write all input combinations here, and then you will fill up the flip-flop input equations from these three equations, and you will fill up the output equation from the last equation here, and then based on your present state and your next state, present state and your flip-flop input, you will fill up the next state equation using the characteristic table that we have derived for a T flip-flop. So this is the procedure. I have just summarized your procedure. So let us see how it has been done. As I mentioned, your present state and your inputs. Then your next state and your output. This we will fill using the excitation equations, and these are our input combinations. What are our input combinations? Starting from 0, 0, 0, 0, 0, 1 till 1, 1, 1. Okay, and so we will fill this one. Next, we will fill this TA, TB. So let me slightly zoom out so that you can look at the equation. Yes, yeah. You can look at the equation here. So TA is x dot b. So TA here is x dot b. X dot b. So 0 dot 0, 0. 0 dot 1, 0. 1 dot 0, 0. 1 dot 1 is 1. Likewise, you will do. What is TB? TB is same as that of my x. So x is 0, 1, 0, 1, 0, 1. So 0, 1, 0, 1, 0, 1. Similarly, y is also filled using the excitation equation A dot b. A dot b is 0, 0, 0. 0, 1, 0. So likewise, last output will be, yeah, 1 dot 1, it is 1. 1 dot 1, it is 1. Now I will fill my next state equation. Please remember that this I will fill at the last. So when I'm filling for the next state A, I will always look at the A for present state and the input equation of A only. Don't get yourself confused because there are a lot of columns. So what is the next state equation? Next state equation is XOR of your present state and your T input. If you want, we can look at the characteristic equation. Where is the characteristic equation of T? So this is the file. I have to look at the other file. JK flip-flop. Yes, this is the exact characteristic table of your T flip-flop. Yeah, this one, this particular table. So when your present state is 0 and your T flip-flop T input is 0, your next state will be 0. So we will use this particular table. When your present state is 0, your T input is 0, it is 0. I think the first three rows are same. When your present state is 0 and your toggle input is 1, your 0 will toggle to 1. When your okay, then when your present state is 1 and when your toggle input is 0, it will be same. It is 1. If you want, you go back and look at the table here. When it is 1 and your T input is 0, your T of T plus 1 is 1. The same thing. When it is 1 and when it is 0, your next state is 1. So likewise, you fill up the next states for A and B. Right? And how did we get this? Is because we got this from we got this from the truth table, in fact. Now, once you know these state equations, then we can draw the state diagram. No need to bother about this particular part. So these are getting the state equations. Okay. So we draw the state diagram from the state table here, and then I have explained it umpty of times. So this is the state diagram that you can draw from the state table here. Okay. Normally, these T flip-flops are used for, and if you want, you can draw the. If you draw the state diagram, also you will end up here only. Okay. So this is how you draw this is how you analyze the circuits, sequential circuits, uh, from the state circuit diagram to the state diagram. Okay. Any doubts here? We have done a lot of examples. Maybe as a last case, let us do one more example with JK flip-flop. Here there are no, okay, there is one input here. What are the inputs? Your X is an input and your Y is an input, and you will have JA, KA as an input equation, JB, KB as an input equation, and this A of T plus 1 will be the next state equation and B of T plus 1 will be the next state equation. Now from the diagram, we first get the flip-flop input equation. So this is going to be JA. What is this JA? JA is equal to B. So we write the input equation. KA is directly connected to B bar. So it is KA is B bar. Then JB corresponds to, it is XOR of A XOR X and the whole bar, which is nothing but a NOR operation. So it is AX plus A bar X bar. And K is same as that of your JB. So we just write it as JB instead of again redoing this. Okay. Okay, so we have got our input equation, and what is our output equation? Y is nothing but it is B XOR of A XOR X. Okay, this is nothing but the sum operation, right? So that is what is your Y is. We all know the JK flip-flop's next state equation, which is JQ bar plus K bar Q. So your next state equation, which means what are the next state equation that you want? You want A of t plus 1 for this and B of t plus 1 for this. That is just a substitute for this. A of t plus 1, you substitute here. It is JA and KA here. And Q corresponds to what? Q corresponds to A, and this Q bar corresponds to A bar and Q corresponds to A. Just to simplify this, what is the value of JA here? JA is given as B. So it is replaced as B. And A bar is as it is. And KA bar, which means that B bar's complement, which will be B. So simplifying this, you take B outside, it is A bar plus A. So your next state value A of t plus 1 is equal to B. Okay. Now, similarly, you get the state equations for B of t plus 1. B of t plus 1, we know that this is the characteristic equation JB dot B bar plus KB bar into B. And what is this JB from the input equation? It is AX plus A bar X bar. AX plus A bar X bar dot B bar. And then KB is replaced with again AX plus X bar, the whole bar, or A bar X, the whole bar, right? Complement of a complement. So if you consider this to be A bar X to be C, some variable, so it will be C bar dot B bar plus C dot B. So what is this? This is nothing but a XNOR operation. So replacing the C with A bar X bar that we, sorry, A XOR X, you get A XOR X dot B, right? So now these are our next state equations. So why did we do this was because this is, if this is a D flip-flop, then you can write directly, or in other terms, because every time you cannot keep remembering your characteristic table, right? Because I asked you to go to page 190. This is not possible in your exams, right? So you have to look at again, go back to this particular table. Instead, without these tables, what we have done is we have written our next state equation in terms of your present state and your input values. So what is A? It is A of t. What is X? This is your input. What is B? It is B of t. So again, now we can write the two next state equation directly from the equations that we derived, which is B of t plus 1 and A of t plus 1, right? So here I'm not going to ask you to go to some page number to look at the characteristic equation. You can just write these characteristic values from the equations that we just derived in terms of your present state and your input equations. So again, the procedure is the same. The first step is fill up the rows of your present state and your input till this one, and then fill up the flip-flop inputs. How do you fill up the flip-flop inputs? JA, values, you can get it from the input equations that we derived from the circuit. This is from the circuit. You fill up JA and KA values. Now, the next state values you can directly fill from this equation. A of t plus 1 is equal to B, right? So you see here that A of t plus 1. So this is what is your A plus means it is the next state, which is instead of writing A of t plus 1 is equal to B, right? So I just copied 0 0 1 1 0 0 1 1 0 0 1 1 0 0 1 1. Otherwise, what is the ideal procedure? Go to the characteristic table, compare your present state of B with JB, KB, right? If it is 1 1, then for 0, there is since your present state is 0, there should be a toggle. You have to look at the characteristic table and then you will have to fill up this one, right? So there is a toggle from 0 to 1. So there is a toggle from 0 to 1. Maybe these two we can see. When JA and KA are 0, we are resetting our flip-flop despite whatever may be our present state value. So we are setting it to 0. Okay. So likewise, you have to fill, which will take a lot of time. Okay. So the first step is you can fill up the Y output because they are independent of your any other value. So Y you can fill it up directly from the this equation, output equation. So that is the first step. Second, third, and fourth step, fill up the flip-flop inputs, and then the last step, fill up from the equations that we just derived here. Okay. Any doubts here? Then once you do this, you can always draw the state diagram, comparing your present state and your inputs. Any doubts here? Next, what we are going to do is exactly the reverse. As I said, I've been repeating it multiple times. What if you are given a state diagram? Then you have to do reverse operation, but it's slightly, it is, I will not say difficult. You will have to remember your excitation table now. So what if a given state diagram, you have to draw the sequential circuit using JK flip-flop? I mean, if they have given that you have to do only using JK flip-flop, then you have to use only JK. Otherwise, you can use any flip-flop of your liking. So what is the procedure I'll tell you? You are given a state diagram. From the state diagram, it is easy for you to get your state table, right? State table or an excitation table. Once you have the state table or an excitation table, then this will be an incomplete table. Okay, this will not give you anything. This for you to get the equations now. So, which means that this table is an incomplete table. So, for example, let us consider this particular circuit. Let us draw the state table for this state diagram. Let us consider the state table for this diagram. So what is that we have? We have present state, we have next state for a given input. If our present state is 0, 0, 0, 0, and if our input is 0, we are in the same state. So we are in the same state. When our input is 1, x equal to 1, we are moving to 0, 1. So we are moving to 0, 1. When our input is 0, 1, when our present state is 0, 1, and the input is 0, we are moving to 1, 0. We are moving to 1, 0. When our input is 1, we are in the same state, 0, 1. When it is 1, 0, and our input is 0, we are in the same state. So we are in the same state. So likewise, we fill up the table. And if you look at this particular table, this is an incomplete table. Why incomplete table? Because you compare your actual state table here and this particular table. What is missing here? What is missing is your inputs are missing. Do we have any inputs here? We don't have any inputs, right? Sorry, we don't have any inputs. All we have, so your flip-flop input equations are missing. And how do you get this flip-flop input equation? In order for you to get it, and what is the one that will relate your present state and your next state, which is the table that will relate these two things? If you go back and see, let me open the previous things. This is JK flip-flop, right? Which is the one that is relating your present state and your next state? I want Q of t and Q of t plus 1. Where is that? We have done somewhere. Yes. Yeah. What is that particular table called? The table is called as an excitation table. So in excitation table, we have our present state, we have our present state, and we have our next state. We can get our JK input. So that is why, if you remember when we were discussing this, I asked you to remember this. So now we have present state and next state. We can fill up what is our J and K inputs. So the same thing we follow here. So we can fill up these columns, using the excitation table that we already know. So we know that we have to fill up this J and K. So we need excitation table. So what we do here is our present state is 0 and 0, and your next state is 0, 0. We have to create these state tables. So what we do is we create a complete state table now. Your present state and your inputs are, as always, it is listed here. The only difference is in the previous case, we first filled up this, then we filled up this. This is the second step. Then this one was the last step. But here now, we are having this first step, and we are having this also. So we can fill it this out now. This we will fill it up at the last, third step. Okay. So that's what we are going to have. So we have our present state, and obviously we will have our input also. These first three columns will be filled up with all possible input combinations 0, 0, 0, 0, 0, 1, likewise till 1, 1, 1. And we already have the next state. This is from your table 1, right? So I'm going to look at this as table 1, that is incomplete steady state, incomplete state table. And I'm going to fill the flip-flop inputs from table 2, which is nothing but my excitation table. So what I will be looking is, when your present state is 0 and your next state is 0, I will go and look at my excitation table. Present state is 0, 0, J and K is 0x. So it is 0x. Again, when it is 0, 0, it is 0x. When it is 0, 0, again it is 0x. When it is 0 and 1, 0 and 1 corresponds to 1x. So it is 1 and x. So likewise, I fill up my all possible entries of my flip-flop inputs. Once I do this, then what is the next step? What is the reverse step? We filled up this from where? From our input equations. So our objective is to get these input equations now. How do we get our input equations from this? Simple, you all know. We will write K-map separately for all these input equations. So for JA, we will write the K-map. So we will fill up the K-map here, which is 0, 0, 1, 1, x, 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 x. So it is 0, 0, 1, 0, x, 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 x. We simplify this, and JA is equal to BX bar. Likewise, for all the last four columns, we write the excitation equation JA, KA, JB, and KB. Once we have these equations, we have everything now. All we need to do is we have to create the circuit diagram based on the equations that we have here. Okay, so JB here is fed from X here, and KB is fed from X XOR A. Right? So A is coming from here, and then it is XORed with your X input. So this is how you do. You design for a circuit diagram, a sequential circuit from a given state table. Any doubt? Okay. Alright, so we will continue in the next class. If you have any doubts, please let me know.